In the last video, you guys understood about behavior of gases, correct? Now let's try to understand how pressure is going to be applied on the walls of a surface because of a gas. Okay. Now here, what we are going to consider, look at this particular figure. Now what you need to understand is that it's in 3 dimensions, correct? The initial position is Vx, Vy, Vz. After hitting with the wall of that particular container, it's bouncing back. That means what we are taking is perfectly elastic collision. No change in the energy or velocity whatsoever. So after collision, we are going to have minus Vx, Vy, Vz. Only the x-axis is changing, y and z-axis is going to be the same. Fair enough? Now, what we are looking at the pressure, correct? Let's try to understand how we can calculate pressure. Alright? First, what we'll do, we'll take that m is the mass of the gas molecule. Okay, very simple. That's the simple assumption. Now, what you have is that the change in the momentum is final minus initial, right? Pf minus Pi. The final is minus m into Vx because of, see, minus Vx, no? So, minus mvx minus mvs, which is going to be minus 2mvx, correct? Now, if that is the momentum or the change in the momentum of the particle, let's try to do the same thing for the wall. Momentum imparted to the wall is going to be plus 2mvx, isn't it? Now what we'll do, say that time taken be delta t. Okay, small value delta t. So the distance traveled will be what? Speed into time, correct? Which is going to be Vx into delta t. Make sense? Now the molecules in that particular path, you're going to have A into Vx into delta t, correct? If there are n number of molecules per unit volume, then you're going to have n into whatever we have done before, which is n A into Vx into delta t, correct? See, now what's going to happen? Understand this one. While going and coming back, that's what we are trying to calculate. But then one way, that is only going or only coming back, if I have to calculate, then the value is going to be this, right? Half of A into Vx into delta t into n, isn't it? The total momentum is going to be what? 2mvx into half into A Vx delta t into n. Half and 2 gets cancelled. So you are going to have mn into A Vx square into delta t. Now what is the force applied? Momentum divided by time. Momentum we know the formula, time we know delta t. So if you apply, this is what you are going to get. Correct? After cancelling delta t. You have mn A, the pressure exerted by the molecules on the wall. What's that going to be? Pressure is what? Force by area. So if you apply the formula, you're going to have mn Vx square. A gets cancelled. See, all the molecules are not going to have same velocity, right? So what we are going to have, we are going to write P is equal to mn Vx square dash. That is the average. Remember, Vx square dash is the average. Same thing is there for Y and Z also. So as the gas is isotropic, you are going to have Vx square bar is equal to Vy square bar is equal to Vz square bar, which basically becomes 1/3 of Vx square bar plus Vy square bar plus Vz square bar. Correct? This can be called as 1/3 C square, where C is the RMS value, that is the root mean square value. So P becomes 1/3 mn C square, or the same thing can also be written as 1/3 m by V into C square, 1/3 rho into C square. Rho is basically the density. Okay, so this is how we define pressure in the gas, or you can say the pressure of gas in the container.